All right. So this is your classic discharging circuit, right? So we hook it to the battery to charge it, and then we flip it over here to discharge it, right? The EMF of the battery is 12 volts, so this is going to be 12 volts, right? And that's going to be our V naught, right? And then they want to figure out the time taken for the charge on the capacitor to fall to 50% of its fully charged value, right? So the charge on the capacitor, by the way, is just voltage times capacitance, right? Is the charge. And so ultimately what we're going to do is we're going to set up this equation, right? We're going to say that the charge is the original charge, e to the minus time over RC, right? Okay. And we know the resistance is 1.2 times 10 to the third, right? That's what the K is, ohms. And then we know the capacitance is 68 nanofarads, right? So C is 68 times 10 to the minus ninth farads, right? So now we know this and we know this, right? We know R, we know C. And then what you do to solve this is it's 50% of its fully charged value. So you're going to say that it's going to be 1/2 Q naught, right? Q naught is the original charge value. 1/2 Q naught is what we're solving for, right? Then we don't need to know that, right? You get 1/2 is equal to e to the minus t over RC. And then just take the natural log of both sides, solve for t. Okay, it's not very long. it's tens of microseconds. Okay, and then this final question here has to do with Faraday's law and Lenz's law. And we don't know how to do it yet, but basically, if there's if this is a coil instead of an ammeter, right, the current is going to start decreasing, right, which causes the magnetic field to collapse. When the magnetic field collapses, it generates an EMF in there because of the changing magnetic field. But you don't know about that yet, so that's not the next unit, but the unit after that. So don't worry about this. All right.